Good evening, ladies and gentlemen. Thank you very much for coming to join us in our hunt for supersymmetric particles this evening. This event is made possible by a European Research Council grant entitled Perspectival Realism, Science, Knowledge and Truth from a Human Vantage Point. So I hope that you will certainly this evening get a lot of science, possibly a little bit of knowledge. And I'm not sure about truth, but we're hoping. This many physicists in the room, that could be difficult. But all of it will be from a human vantage point. Just to help us out, would you mind awfully if I asked you, are there any physicists in the audience? Okay, that's what you're up against.
That's enough to keep us honest.
Yeah, so they'll have to tell me. Okay, that's good. Thank you very much for coming. Supersymmetry. I'd like to say it's a simple idea, but it's not. I mean, all scientists aspire to simplicity. I'd say supersymmetry at the moment is elegant, but it's certainly not simple, but not yet. It's also, I think, fair to say it's controversial and contested, which makes it very exciting, particularly at the moment. I'm sure I'll be corrected, but I think broadly there are two problems facing supersymmetry at the moment. One is there's a veritable forest of hypothesized particles, such as squarks, to name but one. And the question is, do all the hypothesized particles really exist? And if so, what do you have to do to find them? And the other problem is that however many particles they're searching for, they have an even greater number of hypotheses all trying to explain what these particles are doing. So when they get some data, the question is, does it indicate they've discovered something? And even if they have, which of the many theories does it support or disprove? So should we be despondent about supersymmetry? Well, my panelists certainly aren't. Because the questions and the problems faced by supersymmetry are already suggesting that beneath the apparent messiness, there may well be a really beautiful simplicity. And the problems with supersymmetry are already, I think, pointing us on towards an understanding of dark matter and possibly even a whole new physics. So to introduce my speakers, the format is I will ask each of the speakers to speak for 5 minutes or so, and we'll go through what I hope will be questions which will sort of illuminate the area. And then I hope there will be plenty of time afterwards for questions and answers, but we'll save them for the end if that's all right. We're very lucky to have an extremely distinguished panel. Tiziano Camparesi. He's the author and co-author of over 900 peer-reviewed articles. It makes you wonder when he has time to read physics. He's a senior scientist at CERN. He used to work on something called the LEP, the Large Electron Positron Collider, which was one of the machines which really proved that the standard model is right, but also proved that it was incomplete. So then CERN had to build a larger collider, the LHC, which he now works on. He's the CERN team leader on one of the main detectors called the CMS, Compact Muon Solenoid. And I think it's fair to say the CMS and the other main detector, Atlas, is it fair to say that the two detectors that discovered the Higgs? Yeah. There you go. Alan Barr, Professor of Particle Physics, University of Oxford, tutor at Merton College. You work on Atlas, yes? So they're on opposite teams. But they're very good friends.
I defected.
Okay, well, I didn't want to bring that up, but he's worked at the LHC for almost 2 decades, is that right? Crikey, that's a long time. What did you do to deserve that? Hunting for supersymmetric particles and dark matter, and is also on the theoretical side, proposed many of the leading methods for interpreting the LHC results, because that is a big problem. How do you determine them? Then John Butterworth, Professor of Physics at UCL, also on Atlas.
Correct. This is the Atlas couch.
He won the Chadwick Medal of the Institute of Physics 2013 for pioneering experimental and phenomenological work.
That's like theory that's too easy to be called real theory.
Right. And basically on the understanding of something, a wonderful thing called hadronic jets. And is it also true that you're mostly concerned with electroweak symmetry breaking and why things have mass? Okay. So if you ever want to know why things are heavy, he's the man to ask. And he also writes a blog on The Guardian, which I can thoroughly recommend. Then we have Monica D'Onofrio, works on supersymmetry, also on Atlas. So Atlas has definitely got you outnumbered.
Well, it takes 3 Atlas guys.
There you go, I told you the whole
So we are set with friends.
Monica spearheads the research group looking for so-called third-generation squarks and coordinated the Top Squark Research Group. That's not the top group searching for squarks, that's the group that searches for top squarks, just to be clear. And she's a reader in physics at Liverpool University, where on your website it says that you're searching for, you explain the phenomena of excess matter over antimatter, the existence of dark matter and dark energy. So no wonder you're busy. And then finally, Michele Massini, philosopher. So we're not all physicists. Professor of philosophy and of science at the University of Edinburgh, so here. Co-editor-in-chief of the British Journal of Philosophy of Science up until 2016. Mm-hmm. Yeah. Currently vice president of the European Philosophy of Science Association. She's written extensively in the area of history and philosophy of modern physics. Currently principal investigator of a project entitled Perspectival Realism, Science, Knowledge and Truth from a Human Vantage Point. I have asked her about what perspectival realism is, and I think you need to ask her too. And that project received its funding from the European Research Council under the Horizon 2020 Research and Innovation Programme, which co-sponsors this event. We have to say that, otherwise we get in lots of trouble. So, having got all of that out of the way, Susanna, can I start with you? We talked about supersymmetric particles. They've been hypothesized on sort of theoretical grounds because of the limitations of the Standard Model. Can you talk us through what some of the limits of the Standard Model are, why we need these particles?
Okay. Yeah.
In 5 minutes.
Yes, I'll try. Well, I presume you're familiar with the Standard Model. It's nothing but the mathematical constructions on which we use to basically represent our knowledge of nature at the most fundamental level. Now, the concept of mass for particles has always been a troublemaker in the Standard Model. The Higgs boson and the Higgs field have basically solved one of the troubles, which is explaining the existence of mass for the particles which we know. But it has introduced another problem. The other problem is that the Higgs boson himself is very special as a particle. It has a mass, of course. Its mass can be characterized by a Bayer term, something which is part of the theory. But then when the Higgs boson moves in space-time, it basically tends to interact with all of the other particles which are around. In fact, it tends to interact with all of the energy levels which are possible in the way he walks through space-time. And when you try to calculate what the mass of the Higgs boson is, you have to take that into account as well, because basically, there is energy and mass are equivalent. So to a certain extent, you cannot simply take the bare mass. You have also to add the energy of all of the other stuff which is orbiting around the Higgs boson. And it turns out that due to the nature of the Higgs boson, it is a spin theory, so it is really a very special particle. It would tend to basically acquire the mass of the highest energy level available. And the highest energy level available in the theories, in the world which surrounds us, is much, much higher than the mass which we have measured. So in order to keep the mass, but we have measured the mass, so we know it is as low as it is. So in order to keep it at that level, we have to go through excruciating difficulties, mathematical difficulties, to be able to tune the stuff which happens around the bare mass in order to prevent all of the other terms from basically adding up and making its mass too big. Now, supersymmetry, with the addition of these additional particles, which is the mirror particles you will hear later about, basically solves the problem. This basically the companion particles bring in a minus sign. So for any particle which we know, the supersymmetric particle compensates and basically takes out this problem of increasing the mass of the Higgs. So it becomes natural that the mass of the Higgs is low. And so that was one of the reasons why supersymmetry became very popular, because it solves in an easy way what would be otherwise a very difficult problem mathematically. Another aspect is also that one thing which the standard model takes, what we call standard model, is in fact accounting for three of the interactions which exist in nature: the electroweak, the strong, the weak, the electric, the electromagnetism, and the strong interaction. Now, the gravitation stands on a side. If you try to put together gravitation and the standard model, basically you fail, simply because they cannot be put together. And it turns out that if you were to find a mathematical formalism which put these two things together, the only mathematics which can do that is actually the mathematics which is behind supersymmetry. So to a certain extent, we have an incompatibility in our modeling, because we have very established general relativity and very established standard model on one side. And basically they seem to be incompatible. Now nature cannot be incompatible with itself because both exist. So to a certain level, people are convinced that once we will manage to put all of these interactions together in a coherent description, there will be intrinsically something which will resemble supersymmetry underneath. These are the two theoretical reasons why people like supersymmetry, and they like it as the theory which they prefer to go beyond the standard model. It has additional advantages. It naturally would explain, it has a candidate for dark matter, and also when people think about how the various interactions evolve when you increase energy, it basically makes unification of all of the interactions almost natural, in the sense that there's some sort of principle that people would like to, is a heuristic principle, that people would like to see that all of the interactions which today we know as being separate were very likely at the beginning of the universe, when the universe was still very, very close to the Big Bang. There would be a single interactions which then evolved into the interaction which we know today. But that is.
Is it in your opinion then that the supersymmetry is the best candidate for trying to bring together the gravitation with the other forces?
It's if you like, the theory, the most and the best understood theory which can go beyond the standard model. It has been developed very, very widely, and it has these attractive features.
Yes.
Now, it's not the only way we can explain things, but the theorists have tried to formulate in order to go beyond the standard model. But it is definitely, I would say, one of the most attractive ones.
Wonderful. In that case, Monica, can I turn to you? Is all the extra particles that we've got a fair price to pay for this theory? Do you I mean, tell us a little bit about these supersymmetric particles.
Yeah, well, I mean, that's a nice way of posing the question. So yeah, the point is that when you, I mean, Tiziano was nicely explaining that you have these additional particles, but maybe, I mean, for the benefit also of the people that are not physicists, I mean, let me try to explain how there are that many new particles. So our standard model is beautifully described by two families, let's say. And the two families, fermions and bosons, are characterized by a quantity, an intrinsic quantity that I teach to my students in the second year, and that comes directly from quantum mechanics, that is called spin. So you have three families of quarks and leptons and the force carriers. The matter, so quarks and leptons, are fermions. The force carriers are bosons. Supersymmetry tells you that for each of them there is a superpartner. And the superpartner, they have funny name because, I mean, for each quark you have a squark, for each lepton you have a slepton, and instead for the force carriers you add a ino at the end. So for gluon you have gluinos, for photons you have photino, and so on and so forth. So it seems a game, but it's not.
You missed out the wino.
We know.
W has the wino.
We know. So the main point is then that you have all these new particles, and so they solve some of the issues that Tiziano was talking about. But we encounter one little tiny problem, is that in pure supersymmetry, the superparticle, the superpartner, should be exactly like the standard model one, apart for this spin, for this kind of intrinsic momentum. And we didn't find them. So nature tells us that supersymmetry cannot really be like that. So we need to break this symmetry in the mass between the standard model particle and the SUSY particle. And here is where one could say the mess begins, or when the fun begins, because at the end of the day, we don't really know what is the mass of these particles, these new particles. We think that they are there, but they might be much heavier than the standard model particles. So that's where the theorists and the experimentalists, they get together, they bring in their fantasy and their expertise, and they try to find many strategies to really try to look on every corner. You cannot leave, choose one direction instead of the other, because you have a certain indeterminism, and so you really need to have a wide strategy for that. When I was coordinating the SUSY group in Atlas, there were something like 350 people looking for all the supersymmetric particles, and it's like 30-40 teams with a lot of graduate students. And I think that we really try to keep as broad as possible the strategy in order to find and to leave no corner unturned. And whether it's worth to say it's better to look for one kind of particle or the other, in principle, we can use some guidances. So, for example, we have used naturalness as guidance. We have focused on searching on those new supersymmetric particles that are tightly related with the Higgs, because we think that it's very important to understand the Higgs, and therefore those are the ones on which we have focused our attentions at the beginning. But it's not the only thing, because otherwise we would put a bias on ourselves, and we would just go in one direction. Certainly another direction that we have considered a lot, and we are considering a lot, is to search for those kind of SUSY signals, as we call them, that where dark matter candidates arise. Because certainly, even if at the beginning supersymmetry didn't have anything to do with the dark matter, so it's really an outcome that comes for free almost, which makes the beauty of this theory, to be honest. But it's very important. It's very nice to have this kind of candidates in front of us that could explain dark matter. So that's where we focused, for example, our attention as well. But so to come back to the question and the consideration, I think that there are certain choices that we can make based on some guiding principle, and we have made them, but without forgetting that all this comes from an a priori, and we shouldn't really just look for one specific path, but also be open-minded, because this is really what experimentalists and also theorists try to do. They really try to keep all the ways open. So I think that is important to consider, besides the beauty of one theory with respect to the other.
Can I just ask a question about the business of mass? So originally you thought they should be the same mass.
Yes.
Do you have a notion of why they're not?
Well, I mean, I guess that it was almost immediate to understand that they couldn't have the same mass, because think about the electron. The electron is very light; you can really see it, and then you would have to expect a selectron, as they are called, with exactly the same mass, but with being a scalar, and this didn't happen. So effectively, it was almost immediate that this was understood, that the pure introduction of this symmetric view of the universe wasn't really valid. So in a certain extent, it's really natural that was telling us that this was not the case.
I think this is it's not really my go yet, but there's a principle here that Monica's alluding to, which is it sounds a bit perverse that you introduce a symmetry,
Yes.
and then immediately say, well, it can't be right, so you break it again.
Thank you.
Yes.
And this is a principle of hidden symmetries, which is actually really powerful in physics and actually underlies the Higgs mechanism as well. And the way it works is you say, well, at very high energies, all these symmetries are there. And that's why the cancellations that Tiziana was talking about, they work, and that's why supersymmetry, in some sense, is there in nature, in that theory, at very high energies. But in everyday life, it's sort of broken. And you can the analogy that I like to I've actually done it on stage once at the Royal Institution. You can get a magnet that if it's hot, all the atoms are jiggling around really fast. If it's neodymium, then you can do this with a Bunsen burner because the temperature's in the right region.
Mm.
And if all the atoms are jiggling around really fast, and there's a complete symmetry, spherical symmetry to the whole system, it's a little ball of this neodymium. But if you cool it down, then suddenly a magnet forms, and you have a north pole and a south pole, because all the atoms align as they cool down, because the energy leaves the system and they all align. And that's an example of what we call spontaneous symmetry breaking.
Right.
And it's a very good analogy for what happens with the Higgs mechanism is behind that. There are symmetries that need to be restored at high energies in order to make the theory work, but they need to be broken at everyday energy in order to let particles have mass. And similarly with supersymmetry, you say it's a symmetry that's there at really high energies, but as the universe cools after the Big Bang, something comes in and breaks it. And there are numerous ideas what can break it. One of them is gravity, right?
Yes, exactly. So in fact, the major complication there also with respect to the Higgs mechanism is that even the theory that are behind this breaking mechanism of the symmetry are multiple, and depending on the approach that you have, you can put together with gravity, or you can introduce some kind of gauge fields, and in every case there is a completely different phenomenology of these new particles. They decay they disintegrate in a different way. They are produced in a different way, and so that's what brings in a little bit of the indeterminism of these supersymmetric theories.
Yeah. So it's for the universe to be as fecund as it is, for the universe to produce us, you need that symmetry to be broken.
Yes.
Right. So it may be a symmetrical universe at its origin, but luckily for us, the symmetry has broken down.
Absolute symmetry
allows us to be.
Right?
Yeah.
If you have absolute symmetry, you have no structure, you have nothing. So we have a broken symmetry.
Yeah, but physicists love studying symmetrical systems because they're easy. Yeah. So we hate doing a really difficult job. So we're experts at screwing up our eyes so it looks simple, it looks symmetrical, and we leave the complications to someone else to look at.
Well, let's
It's funny because you put it in a hidden field. Usually that's what you do. It's a hidden sector.
Well, let's come to you, Alan. Can you tell us then about talking about screwing your eyes up to make things look the way you want to? Some of the methods and the modelling practices that you and your group at Atlas have devised for finding the information that we want.
Sure. So there are a very large number of theories out there that can both explain the observations that we've got, can incorporate the standard model of particle physics, and can predict things beyond, including things like dark matter. And any theorist worth his salt, and some even who aren't, can put together models that his or her salt, I really should say, can put together models that can extend the standard model to include dark matter. And so the problem is not that there's a dearth of these theories. The problem is that there are far, far, far too many of them. And so the job of any decent experimentalist is to go away and work out how many of these models you can kill.
Right.
using movements that people in this panel have made and others, we've gone away and we've looked at a broad class of models that were all viable before we turned on the Large Hadron Collider, and many of which are now dead as dodos because the data have definitively disproved that that is the way that the universe works. And so science progresses not just by finding something which is definitely there, but by ruling out a lot of other possibilities. And the LHC, even though so far it's only taken about 1% of the data that it intends to take over its lifetime, has already been extremely powerful in exploring the space of these models and ruling out a very large fraction of that space. You know, depending on how you define your metric, I would say really about 40–50% of the interesting space is now dead.
Right. How much of it do you have left to explore?
Well, unfortunately, the
60%.
I was just checking. I know physicists and statistics.
I'm gonna have to wriggle here. So I said of the interesting space, right? So that's the space that's interestingly, subjectively interesting to me now.
Right.
Now we can cover a lot of.
See how this works?
In the next 20 years. But then some theorist will come along and say, But you know, this is their job. They'll go away and say, look, you haven't considered the following class of models, and of course the space of models is unbounded. You know, it's the space of ideas.
Yeah.
And so the space of ideas is huge. So someone can perhaps come up with an idea that's something that we haven't considered so far, and then it's our job to go away and kill that as well, or perhaps prove it to be the case.
The reality is that we look for the thing which looks simple first. And we haven't found it. So now the job is getting tougher. It's not only 60%, it's the tough 60%.
The other half is definitely a lot harder. Yeah.
Right, so you got rid of the obviously false ones.
Well, the ones that were, you know, when you lose your keys, you start looking under the lamppost first. Not because that's necessarily where you lost your keys, but it's the easiest place to find them. So we've looked under the lamppost and we're now starting to look beyond.
Has there been any pattern so far in the theories that you managed to get rid of? Are you able to push the broader community saying it's going to be this kind of an answer and not that kind, or not yet?
Yeah, so the ones which we've been most able to rule out so far are those in which you would produce a lot of the particle of interest, the partner particle, and some of the partner particles are more frequently produced inside the theories than others. So the ones that interact through the strong interaction, the thing that holds the proton together, these are called the squarks. And the gluinos, these are the guys who would be most frequently produced. And so we can say, with pretty much definitiveness now, that this gluino chappie, or chap S, is at least 1,000 times heavier than the proton, or so.
Wow.
And so we've made some pretty definitive statements about that now. Now, okay, someone will find some rigmarole, but it's really difficult to make it that it's not.
So you are beginning to put upper and lower bounds on how heavy or how energetic
lower
particles
bounds
that you're looking for.
Lower bounds.
Lower bounds, not upper bounds.
Upper bounds are really hard. Thing is, right. upper bound in the mass is it can't be heavier than such. But the Large Hadron Collider only has so much energy,
right.
And so if the particle is very heavy, there's just no way that we can produce it, and we don't have sensitivity to it. And so part of the difficulty of this is that you can never guarantee in the game that we're playing at the moment that you can cover the whole of this space, because you would need a collider the size of the universe to do it.
On the other hand, if you want supersymmetry to solve the problem of the Higgs mass that Tiziana mentioned, then it has to be not too far away from the Higgs mass. Mm-hmm. Now, not too far leaves wiggle room, I agree, but an order of magnitude is already getting quite high, and that would be close to where Alan said for the gluino, for instance. So.
The thing of the gluino is in fact one of the most remarkable results actually that we had in the last, from the round 1 and the round 2 of the LHC, how we split those years. So this is from the first start of the LHC back in 2009, 2010. And yes, it's true. I mean, it took actually an enormous effort to get to this answer, because it really meant we are talking about several, like 20, 30 different kind of analysis that really looks at different perspective, and that is probably the only case in which we have at least reached the point in which we can say, okay, up to here it's clear that this is not the case, that this particle it's not here, and I think this is something that I consider this okay. It's not as nice as this, to discover that, but it's as interesting as I mean, it's also very, very interesting to know that it's not there, because it closes a lot of those possibilities. It's not the easiest thing, but things that we thought that were quite plausible before the beginning of the LHC. So in a certain extent, this makes it a very, very interesting result.
John, can I ask you, can you tell us a little bit about some of the experimental challenges of collecting and measuring some of this data at the LHC? Because it's not like just stamp collecting, is it?
Not really, no. Yeah, sure. I mean, we've been talking about this from a theoretical point of view, and it maybe is worth just stepping back and looking at what we actually have in Geneva, which is this 27-kilometre tunnel underground full of superconducting magnets that are steering and controlling and focusing the two highest energy beams of particles that we've ever managed to create in the lab, beams of protons going in opposite directions, and bringing them into collision in four places around the ring, two of which are surrounded by Atlas and CMS, which you can think of as being high-powered digital cameras, really, to record what happens in these collisions. So there are lots of challenges associated with that, one of which is getting the money to do it in the first place, and the other is getting all the people who need to work together to make it happen to work together and stay working together, and not to have too many meetings. But then, the protons are very small, so making them collide is very hard. We have these, they come in bunches, 2 centimeters long, thinner than a human hair, piled through each other with billions of protons in them. Most of those protons miss and go around and have another go. Some of them will collide, and it will be more than one pair that collides, so typically 50 or so now in the LHC collide. So you have to sort out what happened in those collisions. You have to unpick 50 different collisions and throw away the boring ones and keep the interesting ones.
How do you know which of the boring ones?
It means you have to define what you mean by interesting, and you have to do it in as unbiased a way as possible, because if you only look for what you expect, you'll only see what you expect, so there's no point doing the experiment in the first place. We have to make a lot of this selection online. The data rates are so high that we couldn't possibly record all of that data, so you have to make most of the collisions are sort of glancing collisions without much energy exchanged. So we save some of them because there's some interesting things you can learn from them, but in the end you've got so many you don't need any more. So you start throwing them away, and you start looking for collisions that produced a lot of energy transverse to the beam. So the protons didn't just glance past each other, but they hit full on and they produce a lot of transverse energy. That's a very general sign of an interesting, possibly interesting collision. Or they produce muons, or they produce Z bosons and stuff.
I just say that, I mean, in terms of what you threw away, it really is, you have to make some pretty big decisions pretty quickly, because you threw away all but 1 in 1,000 of your collisions. They're happening 40 million times a second, and you've got to make the decision of which 1 in 1,000 you're going to keep within 2 microseconds, right? After which you get another.
You must have very fast reactions.
Couple of minutes. Yeah. So to work out which, and then you threw away all but 1 in 100 of those. Right, so you've got 1 in 10,000, 1 in 100,000 or so of your collisions that you're going to record, and you've got to make rapid decisions. I mean, of course, the computers make the decisions based on algorithms that we tell them, but clearly the idea of what is it that we think is interesting has to be plugged in from the beginning. Otherwise, we're not going to be sensitive to the things that we're interested in.
The point is that we're not throwing these things away because we want. Simply, we could not afford logging all of it, because John was talking about an high-power camera. It's like an 80-megapixel camera, which takes 40 million pictures per second. You multiply to get a data volume which is 3 times the internet of all of Earth. So it is not feasible.
That's your quotes from Google Drive gone immediately.
Exactly.
Well, internet will catch up with us in 2019. It'll be 1-to-1. But now we're still winning.
I just wonder, is it worth, do you want someone to tell you when these things collide what's actually being produced, or is that all clear to you? No. Okay, I mean, because basically I'm going to start and then I'm going to hand over. There's an enormous amount of energy being produced, And when that energy collides, you convert it into mass. So what they're producing are particles which you can't find at Marks and Spencer's and Sainsbury's. They don't exist, and they haven't probably existed since the beginning of the universe. And then they break down. Okay, over to you.
Yeah, no,
whoever wants it.
That's a pretty good start. That's basically what happens.
But then relate that to the particles you're looking for.
So the protons are essentially a bag of quarks and gluons. Okay, they're three quarks in essence bound together, and that's what makes a hydrogen nucleus. So we get them from a bottle of hydrogen somewhere. So when they collide, if they just collide and they smash the protons up, that's not actually that interesting to us because we know about quarks and gluons already. What we care about is a collision between the quarks and the gluons themselves, and we want them to hit really head on. So there's a lot of energy exchange between them, and that's when you really can create completely new particles. So for instance, if you get a quark and an anti-quark annihilate with each other, then you can produce a Z boson, or you can maybe produce an even heavier copy of the Z boson. Or if you get a pair of gluons annihilating with each other, then you can actually produce a Higgs boson that way. That's the most common way of producing a Higgs boson. And then that will decay basically instantaneously, 10 to the minus 20 something in the second.
10 to the minus 20. That's
very, very quick. Yeah. So we don't have a little jar full of Higgs bosons that we took to the Nobel Prize Committee. They've all decayed, but they decay in characteristic ways, and we measure their decay products. And from their decay products, you can reconstruct that they must have been in there. Otherwise, you don't get the data doesn't look the same. So that's the kind of process that we're doing. And it's those distinctive decay products of interesting particles that have been produced. Those are the things we're trying to select on very quickly in the detector.
So you have to find those amongst the trillions of little other particles that are produced and try and sort them out.
To give you an idea, the probability of producing anything else is 10 billion times higher than producing a Higgs boson. So for every Higgs boson...
That's a very large haystack, isn't it?
Yeah.
We dream of needles in haystacks.
So can I just add that
Sure.
for the problem of supersymmetry, it's actually even harder than the problem of the Higgs boson, because when you accept this challenge to go away and look for this stuff, someone's saying to you effectively, look, I've got this theory, it predicts this particle, it may or may not exist, I'd like you to go and look for it, oh, and by the way, it's invisible. So, because if it's going to be a candidate for the dark matter, it's going to be something that doesn't interact with everyday objects. Otherwise, we'd be seeing it bumping into us all the time because the universe is full of dark matter.
Allegedly.
Let's, for the sake of argument, agree with the statement that it might be. And so, if this particle does exist and is responsible for dark matter, then you're faced with the problem of seeing a thing that doesn't interact with the detector apparatus that John has described. And the only way in which you can infer that it exists is because in your particular collision you saw some stuff went spewing out one side of your detector and apparently nothing went the other way at all. And you know that doesn't happen with billiard balls, and we haven't observed it happening with any other particles so far. There's principle called conservation of momentum that means that stuff should go equally in opposite directions. And so if you don't see something going the opposite way, then you infer the thing was invisible. And that's the way that you gain your insight that this invisible particle was produced. So that's what we're challenged with trying to find.
It's even worse because we do particles.
Oh yeah.
Because there's neutrinos, where actually the existence of a neutrino was inferred in exactly that way from beta decay. And we produce those. Right. So, but we know how many to expect. So what we're even looking for, and we know what the rest of the event should look like in a neutrino production event. So we're not even looking for missing things. We're looking for missing things that are missing in a different way from the neutrinos.
All of which will explain to you why Michaela got interested in this, because she thought, put that many physicists together and it just turns into a big mess of particles that are invisible and you don't know where they are and what they're doing and who they belong to. So then you've got to get a philosopher involved who's going to try and sort it all.
Simply says that it took us 2 years to find the Higgs boson. Yeah. Will take probably longer to find the dark matter if nature is kind with us.
Well, there's a good side to that. There's no unemployment looming. So, Michaela, can you... You've looked very closely at the kind of work that these people do. What do you think are the exciting philosophical aspects? Because there's a whole sort of way of looking at this, which is just not obvious.
Yeah, absolutely. So I'm the odd one out, so I'm the philosopher in the panel, and what I do is kind of look at philosophy of science, and there are lots of things you can do when you look at philosophy of science. You can consider different branches of science, and kind of my area is really history and philosophy of physics. And what's really exciting about the LHC physics and the work that people at CMS and Atlas are doing is that kind of challenges the boundaries of our really philosophical ideas on what it means to run an experiment, what it means to come up with a new theory, what it means to make progress in science in a way. So there are loads and loads of interesting philosophical aspects that one can study and analyze from LHC physics, looking at what are the data and how do we make inferences from the data to the phenomena, what are the phenomena and how they are somehow at the end of a very, very, very long, sophisticated chain of theoretical assumptions and modeling practices that people are making. So that's what I'm interested in. I'm interested in those practices, those modeling practices, because they really, I think, in a way, force us to rethink what science is about, in a way, and entrenched view that we may have about why is it that scientists build theories and model, and what's the purpose of building a theory and model. So if you just go around this museum, I'm sure if you go to the second floor of the Science and Technology galleries, you might have seen lots of examples of scientific models. So we have examples of the fourth bridge, I think it's on the second floor on the gallery at the other end. We have models of the DNA, which is in the Earth in Space gallery. So if you think of it, we are accustomed to this idea that really you have one object, say DNA strands, and we build a model. And if you get it, I mean, if you get it right, if you build the right model, obviously you're gonna win the Nobel Prize. That's what Watson and Crick did. And you have one model, right? You have the DNA model that tell us the what we believe is the correct, right story about the structure of the DNA and how it works, how it replicates. Now, what's happening at the LHC in a way is similar, because what we're trying to do is we try to get to the bottom of what are the fundamental constituents of nature. Do we need to go beyond the standard models? Do we need to supplement the standard models with all those other particles? But we are effectively modeling the unknown. So we have good theoretical reasons for thinking that there are all those objects that Monica was describing, but they haven't been found yet. And for all we know, we may or may not find them. Hopefully we will, but what is interesting is that we may be modeling effectively a space of possibility that will still be important for science and for making progress in science, precisely because we are trying to understand what is possible within the parameters that we have, which are basically our best guesses in terms of theories and our best evidence in terms of measurement. So the plurality of models that we were referring to, there are a variety of techniques, absolutely bewildering variety of techniques that they're using in searching for those particles. But even within each modeling practice, there is a completely mind-boggling number of what they call models, which are very, very, very different from the sort of things we tend to think of as models, like, as I said, the fourth bridge model, or the DNA model, and so forth. And so it's this pluralism about model. Well, there are so many models, and sometimes the models that can be very, very different in terms of, I don't know, the value they may assign to the mass of those objects, or the way they describe the decay of those objects, and so forth. And attempting there would be to say, well, we need all those models because, yeah, we're trying to get calculations down, and they function so far as they function, and then we throw them out once they finish their job. But to me, the importance of those plurality of models is because they actually map the space of what is possible, and they provide a guide for genuine scientific discoveries, and we need the plurality. And it may well be that we need to live with that plurality, and it may well be that there may not be one final right answer at the end of the day, that the pluralism is not just a kind of necessarily a transient phenomenon towards the final unique story about nature.
How would you physicists feel about the idea that there might not be one final model which is maps directly one-to-one onto reality, but that you'll need to keep different models. Does that strike you as a hideous outcome, or one you're willing to live with?
Well, take one thing at a time. For example, one assumption which you're doing in order to simplify things is that dark matter, if it is a particle, all of the dark matter universe is explained by a particle, one particle type. Now, it might be that there is 2 or 3, but well, you want to find the first one first. Start discussing about it.
I think I'm very relaxed about the idea that there isn't a final theory of everything. You use 2 words. You say there's one, and you said final.
Yeah.
I'm very relaxed that there may be no final theory, and I don't really care about that because I think there's a progression. Each theory, there's progress. So each one is better. I don't care whether it's the best possible. I just want it to be better than the old one. It's fine by me. And to me, that's a very rewarding endeavour and has been throughout history, and is personally rewarding as well. I am bothered about the idea that a plurality itself will exist forever, because I think that means we don't know. I mean, there always will be a plurality of models beyond where the data can discriminate. But I'm interested in the data discriminating. And I don't think that we want a plurality of models that all describe the same data with 4 different models and they're all equally valid.
That would offend you?
But that would bother me, and I would want to look for a way of deciding which one of those was best.
Right. So you are a realist?
Well, it's also what has happened in history. I mean, if you remember discoveries like, the tau lepton.
Yeah.
There was 6 months of complete chaos on the theoretical side, because basically one had the experimental evidence of having found a new particle, but before figuring out that it was the heavy sister of the muon or of the electrons, people came up with end theories, which basically were successfully proven to be incompatible with what we were observing. And eventually the thing settled onto having an explanation.
I mean, Michaela mentioned actually in an event we had this morning that nuclear physics has this problem that there are at least four different models of how you would calculate what's going on in an atomic nucleus. Mm. To my mind, that's not a problem. I mean, it is a problem for nuclear physics. It means we don't understand the nucleus very well, actually. From a particle physics point of view, they're not models, they're approximations. Mm-hmm. And we know the model is QCD. We know the strong force, it's a standard model, that's what it is. It's just that there are technical problems in solving it, so we have these four different approximations that sort of work to get you phenomenological results out. I'm relaxed about that. If I was a nuclear physicist, I'd be working hard to have a better way of doing the calculations, but I'm not too bothered about the underlying physics, because the underlying physics is a strong interacting still. We understand that. So if we end up with something that, if we have 3 or 4 different ways of stabilizing the Higgs mass and providing dark matter, to me that's not a satisfactory. That's where we are. We have more than 3 or 4 billions. But that's not a satisfactory outcome. That's not an outcome. That's an intermediate stage, and it means you need more data, and you need to kill more of the theories, and you need to find out in the end which is the best one. Now that best one it won't. I'm not saying it'll be the final one. You've killed all the other ones next to it. But I'm quite happy in serial to have multiple theories. But when they're in parallel, then you need more data.
Sorry. Just a clarification on this idea of pluralism, because I think there's pluralism and pluralism, and I think probably the sort of idea that bothers John is the idea that, well, surely there must be 4 different models of the atomic nucleus. I mean, just for reference, this is a previous conversation that we were having, and so. If you look at not supersymmetric particles, but just more kind of mundane objects that we think we know better than supersymmetric particles in terms of, they've been around for a longer time than supersymmetric particles, like the atomic nucleus. Even in that case, there's a pluralism of models. So depending on what phenomenon you're trying to model, you come up with different models. So if you are working in nuclear fission, you might be interested in the liquid drop models. If you are a chemist, interested in chemical bonds, you use the shell models. If you are doing particle physics, you use the QCD model and the quark model.
But importantly, none of those models are incompatible with QCD.
Mm-hmm. Right.
So they're not in conflict. They're just technically convenient ways of solving QCD in a given approximation, but none of them are incompatible with QCD.
I guess the question is, when you say they're not compatible, is the question that arises to me is the question of reductionism, in the sense that if you want to do chemistry and you want to explain chemical bonds and valence, you need to use
quarks are no use.
Exactly, that's what I'm saying. So there are different domains of inquiry where you need those different models. And so saying, well, of course we know what the real structure is standard model is QCD, still doesn't mitigate the problem that we have a plurality of contexts where different models seems to be applicable. And then the question is, okay, what do we do with those models, right? We take just one, the QCD one, as the final true answer to the question of this atomic nucleus, and the others are just convenient tools to describe different phenomena, or do we give a...
There are approximations of the consequences of QCD.
But so is everything. I mean, so you say that the standard model describes the entire universe and it can measure things to 1 part in a billion, and it's a perfect theory, and that's true. But it doesn't, help you cook a good scone, or right bus
or even pronounce it.
The right model is a very much context-dependent thing, right? Yeah. And the fact that we're understanding, or we claim to be understanding, or philosophers might tell us we're understanding, if you like, the basic building blocks of what the universe is made of, doesn't. I think it was Feynman who said, you're working out how the chess pieces move around on the board. That doesn't make you a grandmaster. And to be a grandmaster at chess.
That's true. And so, this reductionism and realism is coming in here. But there's no, basically, as far as we know, the weak interaction and the strong interaction have not much to do with chemistry. And so, if you, with electromagnetism, quantum electrodynamics, you can, in principle, solve most of chemistry and then probably most of the biology and the rest.
Oh, hang on.
But it's obvious that I was playing devil's advocate there, because I don't believe that's true. I think there's emergent behaviour, it's important physics. Even the laws of thermodynamics don't depend on the standard model or emerge from it in any obvious way.
We're about to disappear into a very, very dark rabbit hole. Once the words reductionism and emergence have been uttered in a room, you have to start to tread very carefully, or you'll never get back.
Someone set the fire alarm off.
Yes. Exactly. So, interesting as those things are, shall we just back up from the precipice just a little bit? Tiziana, can you rescue from this? Tell us some of the latest stuff coming from CMS experiment, just to get us right back to supersymmetry, away from reductionism and emergence.
Well, CMS and that as well. Obviously people have been looking for signature for supersymmetric particle production. And as I was hinting earlier, I think we have gone through all of the easy stuff. All of the low-hanging fruits, if you want, have been looking, and there's no low-hanging fruits. So now we are up with trying to explore the space of parameters of supersymmetry, looking for more difficult final states, if you like, or ways of the way supersymmetric particle could appear. There are many different directions. Like, for example, there are final states where basically what you see from the production, from these decay chains coming from supersymmetric particle productions, are such that they really resemble standard model final states. So it ends up, where you basically are producing a top quark. What is left over is top quark and basically almost nothing else. Or where you are not producing almost any visible energy into the event, or you are left with the Z boson. So to a certain extent, you go back to a level where even doing very high precision measurements of standard model productions might actually tell you that there is something which doesn't fit, something which is produced on top of what you expect from standard model, even though they look like particle productions of standard model particles.
So you just need to be more accurate to see the
missing bits. You need basically to accumulate a lot more statistics in order to be able to compare with what you expect theoretically, to see that there is even a small differences with respect to.
And when you say small, you mean very small. So
Well, smaller than what is the statistics which we have today.
So yeah, it depends. It's a few percent, and it's fractions of a percent. It really depends on the particular channel.
Exactly.
On the process that is
Yeah,
concerned.
on what process.
Now, the other area which we are looking at is basically looking. Until now, we basically have explored what Alan was saying is the high rate production of supersymmetric particle. I mean, what we call strong production, so production through strong interactions. Now, there are other ways of producing supersymmetric particles, which is through, for example, weak production. Now, that is intrinsically making the productions the rate of production a lot smaller. So, if you like, that is one area where we are trying to look for rarer and rarer events or signatures of supersymmetric particles. And there are as well developing techniques, experimental techniques, where basically allow us, for example, to better analyze cases where you might have a very massive supersymmetric particle, which basically decays, decays into particles which are then merged together, which you cannot, with the standard techniques which we have used until now, you cannot distinguish space-wise. So we are basically developing new methods, for example, for looking at boosted objects and see whether inside the boosted ensemble of particles which we are seeing in our detectors there is structure, and possibly structure which might be hiding information about the production of supersymmetric particles. And another thing, and I think the other way is also there are parameters in supersymmetry which basically might generate particles which basically tend not to disintegrate as fast as we were talking about. So in other words, this particle would start flying out and having a finite lifetime and decay after a certain space, having gone centimeters, for example. Normally, these particles decay immediately. They travel microns.
Right.
Now, but there might be one, and basically for those it's basically something which we are well equipped to do. Now, in our methods, now we are trying to look as well for things which are basically decaying further away, and looking for possible particles which travel centimeters or even half a meter, and then
and it's the supersymmetry theory which suggests you that
there are certain parameters in supersymmetry that basically would say that the supersymmetric particle which you generate are the ones which basically do not decay very quickly, and this sort of thing. So we are basically looking into more and more difficult topologies, things which we've not looked so far.
Difficult topologies. Okay.
Topologies means.
That's okay. That's all right. At the risk of giving everyone a thumping headache, Alan, can you tell us?
I'll just get my coat.
Some of the work from Atlas, then, because you're working on this phenomenological supersymmetrical model. It's even difficult to say it.
Well, I mean, all we're doing
What does it mean?
is exploring the space of possibilities, right? So we've said, let's imagine that supersymmetry might be right. Let's look to see what ways the particles that Monica is talking about might be produced. Let's look to see how they might decay. And let's just do this as broadly as we can, with as little prejudice from our theoretical friends as we can. Other than that, we're exploring this broad class of models. And so taking that rather agnostic approach within the framework that supersymmetry might be right, we just threw a lot of random numbers at a computer and got them to calculate the consequences that we would see at the LHC if this model was right, or if that model was right, or that model was right. And we, without really very much prejudice at all, picked models at random, and we did this 300,000 times to see what, in general, out of these models you would expect to be able to see. We find that we have actually done a pretty good job, as Monica was alluding to earlier on, of covering quite a lot of that space. But some of the interesting things that come up from this is oh look, there's let's say a region in this area here which you haven't explored as well as you think you might have done. Or actually that analysis is not doing the good job that you thought it was over here. And so in terms of how we're using these models, I think Michaela's right. There's a plethora of even within the general area of supersymmetry, there's a plethora of models that we're exploring. We don't really, well, any of them could be the ultimate description of the universe, but probably they're not. But what they are very good at doing is directing what we as experimentalists should be doing next.
Right.
Where is a good place to look next? Where have we done a good job? Where have we not done?
So you're mapping that area, saying this area is full of theories which aren't working, and here's an area where we think it'll work.
Yeah.
Okay.
And so so what's wonderful about these you pick a model and you can say, well, what would be the consequences of that? Because what's the mass of the gluino? Have we excluded it because of that? What's the mass of the Higgs boson? We know what the Higgs boson's mass is. Can we exclude it for that reason? How much dark matter would it predict? Is it overproducing dark matter that would close the universe and make it collapse too quickly? We can throw those ones away as well. And you can go through this process again and again and again.
So you're sort of the grim reaper for models, aren't you?
Well, let's be honest. Textbooks are full of models that are right, and that gives you the false impression that is the way in which theories work. But even historically speaking, that hasn't been the case. Right. Before there was an inverse square law of gravity, the law that Hooke first thought of for how does gravity work, it went like 1/r rather than 1/r squared, and they discovered that didn't work.
How ridiculous.
So he suggested to Newton to do 1/r squared. That is you have to think of the different ideas before you can kill the ones that are wrong.
All right, well then, can I come to you quickly, Monica? Before he disproves the top quarks, can you tell us what the importance of it is? Because a couple of people have mentioned it. Is there something particular about the top quark?
Well, the top quark, first of all, I can confirm for everybody that is there, has been discovered in 1995 in Chicago, actually, at the Tevatron. It has been looked at for a long, long time. And it's I think it's a very, very good example of one of those things that complicate in a certain extent our searches for new physics. Because the top quark that now we know it's there was new physics before it was discovered. Now, the difference there is that the standard model, in a certain extent, was predicting that there should be this sixth quark, but we didn't know where it was. So in fact, there was, I think, 3 or 4 machines and different accelerators that were built before at the Tevatron, because before they thought it was like 10 GeV, 30 GeV, 40 GeV. Then it was found that 172.4 giga electron volt, which is an enormous number. It's as heavy as a gold atom, pretty much.
The one particle.
So it's really, really big. But it's a fundamental particle. So I think that the top, in a certain extent, it's almost like it's a successful story. But it's also the story of something that we thought we had an hypothesis, but we didn't know exactly where to search, and so physicists they really went after that. Now here it's one particle. Of course, supersymmetry is a little bit more particles, so it's a little bit more complicated. But now the top also it plays an important role also in searches for new physics. Exactly because it's the heaviest one, and it's so heavy that this makes it very, very special. It decays that it's in 10 to the minus 26 second, I think. So it's really, really fast in disintegrating inside the detector. And when it disintegrates in such a way that it produces at least a spray of particles of quarks, and which we see as jets in the detector, and then sometimes in a W boson that on its own it decays, it also decays, and it can be in either quarks or leptons plus these neutrinos. And now these neutrinos, if you remember what Tiziana was saying, they are also invisible, so they look exactly like dark matter. Now, from this very, very broad description, imagine a head-on collision. You have the top are produced in pairs. You have one top, an anti-top on the other side. Then they decay and they produce this spray of particles. Now, I can tell you that the way in which this kind of processes look like, it's very similar to many of the supersymmetric processes that we are searching for. So it's really, really hard to beat. So the discovery of yesterday is what we need to kill now, but the properties of this particle, which are beautifully described by the standard model, can be used in order to analyze, to perform our analysis in a more let's say, efficient way. And so we can use the property of that to distinguish the top from the supersymmetric particle. So we really, I think in the last few decades, there have been many work by the experimentalists and theorists together, the phenomenologists that John was talking about. So these ones that they sit in the middle. And so really studying and taking a simple principle, I mean, basically the equivalence between energy and mass and the conservation of energy. So based on that, we arrived to define certain quantities that are really useful to make us distinguish between the top quark events and the SUSY events, and try to really shed some light in that. But I think that the role of the top quark is also very, very important and is interesting on its own, and that's why there is an all amount of studies that study the precision of this kind of the precision, for example, of the top at the LHC, because measuring, trying to measure as precisely as possible, we can then compare the results of these measurements to the expectation, and if there are deviations, then we would know that there is some kind of new physics. Maybe not exactly what we are looking for, maybe something new, but I mean, as physicists, I think we are quite open to new things, and so we must be open to new things, and so we really, really try to be open-minded in that. So I think the top works has really a relevance from different kind of perspectives. So
it's some landmark we can hang on to amongst all of this invisibility and uncertainty. John, I've heard you talking about model-independent searches. We've talked about how there's, and particularly about how there's just way too many models. So, how does being model? Well, first of all, what is model-independent? How's it help?
It's more that we've gone to all this effort to collide these protons, and one of the reasons to do that is to kill a lot of theories and to hopefully establish a subset of good theories, maybe even one theory that work. But I think we'd all be a bit depressed if the end result of all this effort on the LHC was only expressed in the parameters of theories that we'd kill. So my point, and that's because every statement that you've made then is in the context of a model, which you've then proved wrong because you ruled it out. Or even the one that the subset that survived, you're still only making statements in the context of those models. Now that's interesting and needs doing, but it should not be the legacy of the experiment. The legacy of the experiment should be the most precise measurements we can make of what actually happened. And that means counting the leptons, the electrons, the photons, all the particles that were produced, what were their energies and angles, where did they go, and measuring that as precisely as possible. Now, of course, when you measure that, you're guided by theories, but the actual result of the measurement itself is not model dependent. It's just saying, we collide protons together, and every 5 minutes we get an event with 4 muons that have more than this energy. There's no theory in that, it's just we did this and this is what happened. You can interpret that and say, and actually the fact that it was this number and not that number means this theory might be right and this theory is definitely wrong. But nevertheless, the important thing is that you counted the muons and you measured it as precisely as you can. So what I mostly spend my time doing is making measurements rather than doing actual searches. And the distinction there is in a search, you start with the model, you look for signatures in the data that model might lead to, and if you don't see them, you rule the model out. Whereas in case of a measurement, you start with the detector and you say, well, what happened? How precisely do I know what happened in this collision? Here's the measurement, so within some uncertainty. And then, in the end, you can meet with the searches and you can put both of those together and say, we know what did happen, we know what didn't happen, all of that is valuable information. But the advantage of the measurement is, in 50 years' time, after I'm long gone, some theory comes along with an idea, some theorist comes along with an idea, says this might have happened at the LHC. If you've got the measurements still on file, you can go and check that again later, rather than it's too late to take that theory and do a search for it directly. But if you've made the measurements honestly and precisely, then the information is still there and still valuable. So that's the kind of, in the end, if you do both jobs well, you end up with pretty much the same result. But I think the shelf life of the measurements is longer. The legacy of the measurements is longer.
Brilliant. Michaela, do you think that there's a philosophical importance to that kind of model independent work?
Yeah, I mean, just what John was saying. Traditionally, we tend to think of science as coming up with a hypothesis and testing, and then on the basis of how that works, we can refute the hypothesis and go on to another one. But in cases where we are trying to model the unknown, and so there's plenty of scope for discovery, and there's a bewildering varieties of models. Model independence is important for having an effective strategy, effectively, of bringing the theoreticians and experimentalists together. It would just be too time-consuming and laborious and ineffective trying to test each and every single model of SUSY available. So the idea of a model independence is more, as I understand it, by talking with all those people, and then everyone gives me a different answer about what it means. This is my philosophical take on it. Is that it's really the place where the theoreticians meet the experimentalists, and in a way it's the place where the experimentalists provide a sort of bottom-up, data-driven approach with precise measurements that tell the theoreticians, don't waste your time looking for sophisticated theoretical models in those areas, in those regimes, because those have already been excluded. So model independence is important in those areas precisely because of all these unknown parameters and bewildering varieties of models, the most effective way of proceeding.
Can I jump in? I'm all on board with John that we should be trying to do things that are not too guided by theoretical models where we can. But total model independence is clearly an ideal, which is impossible, and I think you recognise this as well. So I mean, you can say, okay, I have to be guided to some extent by the good model I've got already, which is the standard model, which tells me how my muon interacts with the detector and my model of the electronics. And so there's lots of models.
But those are things we've measured already. I mean, we have data.
That's right.
So.
But it's also the case that when we do even the most basic interpretation, it can be the case that what we thought was a muon was not really a muon, but it was a new particle that travelled through the muon detectors in the way that we thought a muon should. And so one should aspire to this model independence as best as one can, but it's always going to be a relative statement. It's never going to be an absolute.
Yeah, I mean, my statement is actually minimising model dependence, which I think is the thing we aspire to. You can never complete.
I'm going to ask them to hold up there for a second, because if you don't, they'll carry on until next week. Can I open it up to some questions? Because I'm sure that what you've heard already has made everything crystal clear. But if there's just the odd little corner that you want clarified, now is your moment. We've got a microphone. Or you could just shout.
I can just shout.
Here.
We have the technology, you must use it.
Since we found the particle wave, does that mean there is a gravity particle? And if there's a gravity particle that we can find, does that mean we can find out how dark matter works? Because gravity has an effect on dark matter.
That's a great question.
Then let's have a great answer.
Well, I don't know about that. So the fact that we observe gravitational waves is actually one of the biggest breakthrough, at least since the Higgs, and it's comparable to that discovery. It's predicted by general relativity, and so it's a massive validation of that theory. But unfortunately, the waves are so long that they don't tell us anything about the quantum nature of gravitation. And so when you talk about, is there a gravity particle, that's talking about, we know that, for instance, light is an electromagnetic wave, and radar behaves just like waves. But if you pump the energy high enough, you get gamma rays, which is still light, but they're like bullets, they're like photons individual. And that's the quantum behavior, that's the wave-particle duality of quantum mechanics coming in, really. That low energies things look like waves, they look classical. At small distances and high energies, they look like particles. The waves that have been seen, the gravitational waves, are very much on the classical end of that. So they're more like radar, they're not like gamma rays. So It's a big step forward, but it's not directly telling us anything about quantum gravity at the moment, and it still leaves us with general relativity passing all its tests and standard model passing all its tests, and still not making the meet in the middle. There are plenty of people, I mean, there's a lot to be learned from those gravitational waves, both astrophysically and basic physics. So I wouldn't rule out the fact that they'll give us some important clues along the lines that you're saying to the way cosmology and the way that matter works and interacts with gravity, but not directly telling us anything about the particle, the graviton, which would be the quantum mechanical analogue of those gravitational waves. They're too low energy to be really telling us that.
On the other hand, we are even searching for the super partner of the graviton, just in case.
there are models in which the dark matter
gravity.
is actually the super partner of the graviton.
Yes.
So, but those waves don't tell us.
Anyone else feeling brave? I think there's a gentleman. I'm not meaning to be rude. It's just I can't tell. Not from here, anyway.
So John touched on this with his comment about crumpets, scones. But what practical real-world applications do you think could be made from your research?
Ouch.
Well, I think none. The none is the simple answer, but I mean, let me try to give you some sort of historical perspective. If anyone had asked Einstein in 1905, when he was basically writing his paper, synthesizing 50 years of measurements before about what was basically setting the foundation of quantum mechanics, if he had been honest, he would tell you the same thing. If he had posed this answer, he would have said none. I mean, he could not figure out what it would be useful for. Now, it took 100 years before the thing gave rise to DVD and Blu-rays and whatever. So, not saying that what we are doing is going to have the same kind of effect, but honestly, as of today, fundamental research is fundamental. It has no other purpose. It should be said that some of the stuff which we develop in order to be able to do our research turns out to be fairly useful.
Like better magnets.
Well, the web.
The World Wide Web is a classic example.
The World Wide Web was basically invented by a guy whom I was working with when I was much younger. And his main work was basically developing code to help us controlling the voltage of muon chambers remotely. And in his spare time, he realized that big guys were spending an enormous amount of time transferring files from 4 different kind of computers which we had at the time. It was digital, IBM, North data computer, and control data computers. It really would take half a day to be able to transfer a file from one of these computers to another. And he basically invented the World Wide Web in order to ease our work in terms of transferring files to a certain extent. Now,
and now you've got Facebook full of pictures of kittens.
No,
that's progress.
But that basically points out one aspect of what we are doing. I mean, we are basically dealing with developing technology in many different areas, from electronics to computing and these sort of things, which is basically for our purposes. And sometimes these things turn out to be useful as well in real life, but it's almost an accident.
I guess
No, I can tell you the electronic chip which we were using in 1990 to read out one of our tracking chambers basically was, we got a call from SGS Thomson saying, can I put this chip on the market? And it was used by Canon to do the exposimeter of the AE1. Now, in that case, only SGS Thomson made money out of it, not us. But this is what I mean, is almost...
I would also say that you're asking the wrong person, because in the past, when we've done basic research, it's been the people who've made the breakthroughs in understanding how the universe works are really not the right people to then go and use that and make money out of it, usually. So there's a kind of ecosystem of people who are motivated by trying to understand the way the universe works, and people who are motivated in building better technologies and making people's lives better or making money from those technologies. And we all, as you heard very clearly there, we operate within that ecosystem. But we're not. If I was a venture capitalist, the last person I'd ask how to make money from the Higgs would be a particle physicist.
Yeah. Actually, you know one thing, it was quite interesting talking about venture capitalists. Once I was taking a guy to visit our experiment, and I don't know how it came to talk about extra dimension. And I happened to basically mention that the only way our world, our four-dimensional world, talks to extra dimensions by transfer of energy. The guy immediately clicked and said, well, if you can transfer energy this way, you can transfer energy the other way. So, I mean, you want to work with me on a project?
Getting energy
from extra dimensions? I declined. But,
in all seriousness, so we don't know. So most of the universe, if dark matter theory is right, is made of dark matter. It's not made out of us. It is, in most of these models, it is by far the biggest energy source in the universe, but none of us have the first clue how we would use it. But we're in good company. Rutherford, whenever he was exploring the atomic nucleus, he famously said, any talk of getting energy out of the nucleus is moonshine. And he meant to say that it's rubbish, it's never going to be happening. But actually he turned out to be right, because he didn't know at the time, but moonshine is, of course, generated from nuclear energy, happening outside the sun reflecting off the nuclear product. So you just don't know. You don't know. But the reason we're in this is not because we want to make our fortune. We'd easier make our fortune elsewhere. We're in it because it's interesting. It's fun.
It would be interesting to hear the philosopher's take on that question.
Yeah.
That's you.
Sorry?
What was your take on that question?
I completely agree. I mean, if you look at, the history of science, the way we'll be remembered in 500 years from now are in terms of advances to the fundamental physics. That's what we remember, right? That's how we remember Newton and the advances from Aristotle. That's how we remember Lavoisier and the chemical revolution advances over phlogiston theory. I mean, those people didn't do it because they had a necessarily practical purpose in mind, that they were doing, if you like, blue sky fundamental research. That's how mankind in any time progresses. And so absolutely we need to invest on fundamental research. And it's how science progresses over centuries. And then obviously there are all those implications that people may not realize straight away, but may come along. But I think it would be absolutely misguided to think that fundamental research is some sort of a second-class kind of research. It's fundamental because it's what really guides progress in science.
Other questions?
So one just at the front here?
Yeah, please.
Much of what has been said to me is blindingly clear, with the accent on the blinding.
I was expecting someone to comment on that. There are 3 Italians in the panel, which is quite unusual.
But it seems to me, from what has been said, that much of your all of your experiments and much of your theories depend on technology. You said perhaps there would come a time when you'd have more accurate measurements. In what way might there be possible technical advances in this way?
Yes. So the thing that limits the energy with which we can collide the particles inside the Large Hadron Collider is the strength of the magnets that bend the beams around into collision. If we had a stronger magnetic field, then we could bend the particles in a tighter curve, or effectively we could bend higher energy particles in the same curve. So using the same tunnels we've got, we could go to higher energy. Now not even we, our predecessors, when they designed the LHC, designed it with the best magnet technology that they had at the time. And magnet technology has moved on since that time, in part because we want to do it in order to build a better machine in the future. And so it's not just the case that we are recipients of technology that happens to help us out. But like with the web, like with the magnets, like with some of the electronics that we're using, in many cases, we're going to industry to say, I know you can't do this at the moment, but if you could do this, then we could build a better machine. They quite often do that for us, even at a loss to themselves, because it gives them additional capability that they didn't have before, that they can sell at a profit elsewhere.
Well, actually, it goes even further than that, because I mean there is the magnet part, but there are other parts of the accelerator, for example, that we are in discussion. I mean, because of some projects that would want to have to build much more powerful accelerator, where there is even, I mean, the industry, then they are coming back saying, betting on the fact that there is going to be a certain number of years, and after that they will do that. And so already planning the construction of something that is not yet there, but there is this kind of plan.
There is also advances which we are basically working on in terms of research and development on the detector side. For example, all of our devices have response times. I mean, we have a time resolution which is pretty good. It's at the level of nanoseconds, billionths of a second. It turns out that we are trying to do 100 times better than that. And if we were managing to do 100 times better than that, we would be able to have a much better selection and measurements of the events of what happens when the collision happens. Now, in this case, by the way, we would have an immediate return in technology. We know it already because, for example, if we were to be able to develop detectors which have 10 picoseconds, so 100 times better than what we have today in terms of time resolution, we would basically reducing by a factor of 50 the irradiation of patients when they do positron emission tomography in an hospital, which is this non-invasive kind of diagnostic for very specific cancer types. So this is the kind of things which is going on now.
It might be worth pointing out that we haven't really discussed money much here as well, but that's an important driver. And the budget of CERN, roughly, is about €3 per year per taxpayer within the EU, and has been pretty much flat in real terms for the last few decades. Yet the capability that we have within that has grown enormously. And some of that is because we're the beneficiaries of background technological development. Certainly Moore's law with computing has helped a lot, that we've managed to ride the back of, we've not been driving processing power in computers for a long time. We were actually at the beginning, but we're not anymore. We're customers for that. On the other hand, the kind of developments that Alan and Monica and Tiziana were talking about, that we are in the mix there, we're helping to drive them. And all of that, the fact that we can't just go and ask for more money, but we have to do more within the same budget, is also a very real pressure that really means we do a lot of R&D, we participate in the R&D, and all of these are good examples of how it may get better.
Do we have another couple of questions?
Just one more.
One more?
Yeah.
Yes? Yeah. I'm sorry if
I was... You're right.
The Mach particles in the standard model look like a mini periodic table. Could there be another layer beneath, giving them the common characteristics?
Yes. We spent far too long discussing supersymmetry. Definitely this is a complete alternative to supersymmetry, that there's another layer of substructure. It's not as favourable, as fashionable as supersymmetry for good reasons. We have good reasons why supersymmetry is more favoured in general, but it's not ruled out by any means, and it may well be the case, yes. There are all kinds of models called Technicolor and things which we won't go into now, but yes, there are plenty of theorists thinking about that. And
there are plenty of searchers also. Well, not plenty, but certainly a lot of them that they are searching for substructure of this kind.
Yeah. And that's an area in which, you know, we've talked a lot about areas where there's lots of theories, and we're trying to solve a problem with having too many theories. This is the problem you talk about here with the periodic table-like structure of the standard model is a case where just no one has come up with the right theory yet. We've got beautifully precise data. We know exactly what the properties of these particles are, and just no one has been smart enough yet to work out what the pattern is.
So with that, if you could jot down your best ideas, just leave them on the way out. I'm afraid we are out of time. I believe we have to finish at 7, is that right?
I think so, yes.
So it just remains for me to ask you if you would join me in thanking our panelists.